Well, this video is supposed to be on the reactions of acid anhydrides, as opposed to the previous one on the video on the reactions of acid chlorides. You'll see that it's really the same. The only difference is that instead of a chlorine being the leaving group, it will be this larger structure. Otherwise, the mechanisms and the products that you'd predict, you would arrive at in the same way. So just to remind you, an acid anhydride is where you have two carbonyls separated by an oxygen. So an oxygen connecting those two carbonyls there. But when you see that, what you want to think of is one carboxylic acid derivative with a gigantic leaving group attached. That's how you want to conceptually organize that in your mind. And so when you're drawing a draft of the product you'll get, it will be an acyl substitution reaction, a nucleophilic acyl substitution reaction. So you can draw a draft by just writing the original part in without the leaving group, and then drawing in whatever nucleophile you have. Now in this case, it's going to be this phenol, just without the hydrogen. You might be tempted to keep the hydrogen in. You would notice that that would give this oxygen 3 bonds, and so a full positive charge. So to stabilize that, you end up doing a proton transfer. And so that's your product. Okay, that's how you would predict the product through synthesis, just hopscotching from the beginning to the end. For each of these, just like in the previous video, I'm going to do the synthesis for the exercise, and then I'm going to, for those interested, I'm going to walk through the mechanism. So if you're not interested in the mechanism, you can scrub to the next place in the video where you see B. If you are interested in the mechanism, I'm going to redraw this just without the benzene rings explicitly drawn. I'm going to substitute those with capital P's, lowercase h's. So they are sort of phenyl branches. So this is our anhydride, and we're going to focus on this one on the left. The truth is you could focus on either of them. This one is symmetrical. They both could react. And our nucleophile, phenol, and specifically the oxygen of phenol, and here on the other side we have another benzene ring, so I'll have that pH there. That oxygen there is slightly negative and can attack the carbonyl carbon in the acid anhydride. The pi bond would break, go up, and you'd be left with a tetrahedral intermediate. So you would have this molecule here. This oxygen at the bottom has 3 bonds and therefore a full positive charge. So that's your tetrahedral intermediate. The oxygen is very unstable, so it would snap back down and kick the leaving group off. Now technically the mechanism for this would be acid catalyzed, and I'm not drawing it that way, just to avoid taking a whole bunch of time drawing a whole bunch of proton transfers. I want you to get a sense of how the reaction happens, not every nut and bolt, because the focus here is really on the synthesis in this exercise. Notice that this whole thing functions as a leaving group, and you'll see why when you see the structure for that. So you could have this. Notice that the oxygen has 3 bonds there, so a full positive charge, and the other thing is this other piece that left is the leaving group. The reason why that was such a good leaving group is because that negative charge, which is coming from these lone pairs, is allylic to the pi bond. And so there's a resonance structure that spreads that negative charge out over all 3 of those bonds. So then we do that, and you can take another equivalent, or you can take this base here actually and just do the proton transfer to stabilize the charges. So this is a sort of broad brush version of this mechanism, but you can see that it's really just a standard nucleophilic acyl substitution. So I'm going to redraw in those benzene rings. And that's the product we predicted at the very beginning. So standard nucleophilic acyl substitution. The only new different thing here is the leaving group, which is admittedly kind of big. But that's the leaving group in the anhydrides. So this next one, you'd look at this, again you'd see an anhydride, 2 carbonyls connected by an oxygen. And so when you see that, you want to organize it as one carboxylic acid derivative with a leaving group attached. And so when you're just trying to think about synthesis, you would redraw the carboxylic acid derivative part, and you'll replace the leaving group with your nucleophile. Here our nucleophile is going to be the nitrogen in this compound. So we'll have a nitrogen, and it will have the two ethyl groups on it. The hydrogen, you may be tempted to put that there. That would give this nitrogen 4 bonds and a full positive charge. The reason why you have excess of it is a second equivalent comes by, does a proton transfer to take that off and stabilize the charge. So that's the product you would get in that synthesis question. So that's the synthesis. Now, quickly, the mechanism for this reaction. The first thing is the nucleophile attacks the carbonyl carbon. So we have these two ethyl groups here and a hydrogen. This nucleophilic nitrogen with a slight negative charge swoops in, attacks the carbonyl carbon, and kicks the electrons in the pi bond up. So nucleophilic attack. After that nucleophilic attack, you would have a tetrahedral intermediate. The oxygen here would have a full negative charge, and here you'd have the nitrogen bonded to two ethyl groups and a hydrogen with a full positive charge. The oxygen with the full negative charge snaps back down, kicks the anhydride off as the leaving group, so that's loss of a leaving group. And so you end up with that leaving group gone. And you'll notice here one of the reasons why anhydrides are not often used industrially. Usually you'd use an acid chloride instead, because so many carbon atoms are wasted. This leaving group is big. It's not a product that we really wanted, and so it's just waste product for this storyline. And so it is not used industrially because it's not as efficient in terms of usage of carbon atoms. You have excess of this nitrogen, this amine, this diethylamine, because it can act as a base. So the lone pair on that nitrogen can come by, steal this hydrogen. The nitrogen here had 4 bonds, and so a full positive charge. When you steal that hydrogen, the hydrogen snaps back onto the nitrogen, and you end up forming a stable amide. So that would be NN-diethyl propanamide. And that is the molecule that we originally predicted we would get in this nucleophilic acyl substitution reaction. Okay, this next one. Now, they're trying to mix you up here a little bit by drawing the anhydride over the arrow, and so it's just a sort of small conceptual stretch. Do you recognize that it doesn't matter whether something is over the arrow or not? These things are going to react with each other in the same beaker, no matter how you write them on a paper. And so you'd see this carboxylic acid derivative, you'd see that it's an anhydride, 2 carbonyls connected with an oxygen. And so you'd recognize that one half of it is going to be a leaving group. The leaving group is going to be replaced by our nucleophile, which is ultimately the oxygen, which sort of brings the whole molecule along with it. Here, you'd redraw the part that's not the leaving group, and just replace the leaving group with the nucleophile. Now the oxygen is the nucleophilic atom, the slightly negative one, and so that's the one that's going to attach to the carbonyl carbon. If you try to keep track of how to draw this, you can number it. And here I'm not numbering it to name it, I'm just numbering it to keep track of stuff. So if the oxygen is connected to carbon number 1, and I go around, on 2 I'll have a methyl group, on 5 I'll have a tert-butyl group. So if I do that same thing here, 2, 3, 4, 5, 6. On 2, I will have a methyl group. On 5, a tert-butyl group. And that's your product. Except this oxygen has a full positive charge, and so you do a proton transfer to remove that. Because the mechanism for this is truly the same as one we've drawn a million times, nucleophilic acyl substitution, the same as the one we drew last time, I'm going to skip the mechanism for this one. It's the same exact steps as we drew above. So hopefully the mechanism for that will make sense if you think through it. So then, in D, we run into a similar scenario. You would notice a carboxylic acid derivative, an anhydride, 2 carbonyls connected with an oxygen. And so when you look at that, you think about the thing that's the leaving group. And when you're trying to draw the product, draw everything but the leaving group and replace the leaving group with your nucleophile. Here the nucleophile is the nitrogen. You might be tempted to just draw that exact molecule with a hydrogen and a 6-membered ring, but don't forget that nitrogen would have 4 bonds and so a full positive charge. So you have to do a proton transfer, and that's why they're using excess here. A second equivalent will come by, steal this proton, and stabilize that charge. So that's the product you get there, and the mechanism for this is the exact same as the one we drew above, nucleophilic acyl substitution, as we've drawn many, many times. So you can see that the reactions for acid anhydrides are really the same, if not a little simpler, than the reactions for acid chlorides. The only difference is what the leaving group is. Otherwise, the reaction happens the exact same as with acid chlorides. These anhydrides are relatively rare. They're rare in living things because they're very reactive, just like acid chlorides are, and they're reactive because they have such great leaving groups. The leaving group is stabilized by resonance. And they're also rare in industry because they're not very efficient. You end up wasting half of your carbon molecule as a leaving group. But here, those are the some reactions of these. And what you should get out of this video is not a comprehensive sense of every possible reaction that could ever happen with an anhydride, not like a recipe for every single one. What you should get out of this video is that no matter what the recipe is, the anhydride, 1/2 of the anhydride acts as a leaving group, and whatever you add is replacing it as the nucleophile. So that conceptual understanding is able to let you understand many, many reactions, even if you've never seen the specific molecules before. You just look for the nucleophile and replace the leaving group with it.